After numerous testings of each design that we made, each design came up with problems that we couldn't foresee beforehand. A lot of problems in terms of like dealing with fits and dealing with bearings and dealing with the rubber bands and stuff. They were entangled, they would get stuck between parts, components that we don't want it, causing a lot more friction, and it wouldn't even, and it had a lot of mass. So we went on to the second prototype, which we cut down the mass, cut a lot more groove, added 2 spaces for the locking mechanism, and we were sure that it's going to work, and it was light and everything, and it had an aesthetic design, had a drag coefficient of 0.24 with simulations to back it up. But the propeller couldn't, cause more thrust to actually propel the device, which allowed us to disregard this design and disregard these propellers because they were too small. And then we moved on to a design that looks like this, but it was smaller at first because this design didn't propel the vehicle to the maximum distance because the rubber bands tested were too small and it didn't have a lot of more steering potential. Even when we added a lot more, it would just cause other problems like snapping and cutting and braking. So we went over and 3D printed a longer design which had a lot more potential for the rubber bands to actually store more energy. And as you can see, the new propellers are really big. These cause a lot more thrust, and the locking mechanism here can support more weight and more loads if you want to. And this design works a lot better than the previous models and previous designs.
So this project is manufactured majority through 3D printing. So this is due to a variety of reasons outlined in our report. One of them was cost. The second thing was design for iteration, so we were able to iterate a lot quickly. Third thing, again, was time. It took a lot less time for us to go through our design iterations. And fourth thing was that we wanted to minimize impact on the environment. Now we also did this through our external materials that we used beyond just 3D printing, because we also wanted to design for portability. We minimized those materials as well, and this included the mounting mechanism for the dropping of the potatoes. As well as the pulley goes, the pulley was machined through lathe, and that was one of the components that we had to adhere to for this project. And other than that, yeah, the entire project was majority 3D printed with minimal impact on the environment, and it catered to all of our design requirements.
For our simulation portion, we decided to do stress and strain simulations on our car body. We mostly focused on 2 parts. One part was the locking mechanism, and the second part being the stand which the bearings and bars are placed on. So to do our simulations, we decided to use SolidWorks. Here you can see the first simulation that we've done, which is the mount. Our fixed points were here and here, and our force is along the top here and here, where our bearings would be placed. As you can see that our max stress is 5.478 to the power of 7, and our yield strength is 4 to the power of 9. This simulation is done using von Mises theory. So this is our locking mechanism. The hole in the middle is where the shaft will be placed, and the hole on the left is where our pin is placed, and the force that is exerted by the pin is shown here. And as you can see over here, it is under our yield strength, so it will not fail.
So here's our design again. First I'm going to talk about how the energy of the rubber band is transferred into the propellers. One thing to note is that the propellers is better to analyze them in terms of power. So the way we're going to be doing that is we're going to divide the energy stored in the rubber bands by the time it takes for the shaft to completely rotate, for the rubber bands to unstretch completely. So the way we do that is actually a bit complicated, finding the time. The first thing we have to do is find the angular acceleration of the shaft. Then from simple kinematic angular equations, we can find the time it takes for the shaft to completely rotate. Okay, so once we find that time, we can divide the energy of the stored in the rubber bands by the time, and we can find what the power of the propellers are. From the power of the propellers, we can actually determine what the velocity of air coming out of the propellers is by a simple formula. Once we know the velocity of the air coming out, we can use a Reynolds transport theorem to find out what the force of propulsion provided by the propeller is. And once we have this force, we can do force balancing. We know that there is a rolling force that is going to be counteracting the propulsion force. So we do the force balance, divided by the mass of the card, and we get the acceleration of the card. Again, using kinematic equations, we can find the distance that the card can travel, which in our case, our objective is 10 meters. One second.